Hi, everybody. This is a lecture video for chapter 11. Title of the chapter is The Dynamic Planet, which is a great way to describe Earth because it is constantly changing. And that is essentially what the term dynamic refers to in this title. The fact that the planet Earth is always changing. And so we're going to look at that change and how it occurs by talking about some of the internal processes that fuel um, plate tectonics, how it fuels the convection that happens inside the Earth, and ultimately how it forms some of the landforms that we see. These are processes that build up the Earth. And so this picture, Cotopaxi in Ecuador, we are looking at our first landform in this picture. And I'm sure we can all guess what's in the background. That is a volcano currently erupting, a big ash cloud that we see in the background there. But that is just one of the landforms that help build up the Earth, and they are formed through processes that start inside the Earth. And so that is the general theme for this chapter 11. And like I do for all chapters, at the very beginning, I go over the learning objectives that we should be able to um, understand by the end of the chapter. And how this is set up in chapter 11 is that first, we will talk about the differences between endogenic and exogenic energy and the systems which are created through these types of energy. We will talk about the driving force for each one, and really focus on their differences. Next, we'll look briefly at Earth's insides. We'll talk about each of the layers that make up the Earth, the core, the mantle, and the crust. Then we will talk about geologic cycles, how Earth really has three interrelated geologic cycles. Those would be the rock cycle, the plate tectonics cycle, and the hydrology cycle. Yeah, we'll talk about how they're related and what each one is, but how they're related also. We will talk about Pangea, uh, and how and how plate tectonics led to Pangea breaking apart and all of the continents that we know today ending up where they are. We're going to talk all about that and how the theory of plate tectonics led us to understand how that occurred. And so we'll talk a little bit about the evidence that and observations that was used to develop the theory of plate tectonics, which includes talking about specifically seafloor spreading. So that will all be explained in the middle of the chapter uh, and towards the end of the chapter. And then we'll end up looking at um, Earth's major plates. And we don't have to memorize any plates on a map, but we do want to um, be able to identify plate boundaries, different types of plate boundaries, how the plates are moving, and how the boundaries of the plates relate to the location of earthquakes, volcanoes, and then we throw in hotspots there because they're related to volcanoes. on volcanic activity. So that's the rundown for chapter 11. We start off with kind of this intro um, about the inside of the Earth. Then we talk about plate tectonics, and then last we're going to talk about earthquakes and volcanoes. This is a little bit of a longer chapter as well. So I may have summarized it very briefly, but um, it's a tiny bit of a longer chapter. So let's start with kind of the intro of the dynamic planet itself, how Earth changes. The internal processes of Earth itself, we call those endogenic. The the beginning of the word endo, that refers to inside internal processes. And so the energy that's fueling the internal processes of Earth, it's the heat. It's heat energy that's coming from the core where we have radioactive decay occurring. There's a good amount of uranium as an element in the core, and so uranium very reactive. It's considered a heavy and unstable radioactive element, and as it decays, it gives off heat. So this heat radiates out from the center of the Earth and is providing the energy needed for mantle convection, meaning that the mantle rocks are moving slowly, they flow slowly, and that's the basis for the rock hydrologic water and tectonic cycles, that interior heat. And not only that, but making of rocks and plate tectonics and water itself is what really just it all creates most of the surface of the earth, um, which our topography is variable. We have mountains and volcanoes. There's faulting, hot springs. That's all directly built by endogenic processes. And that's those are the pictures in at the bottom of the slide here. We have volcanoes, there's hot springs, and these mountains here uh, are made um, through faulting. So when we're talking about landforms in just as a whole, all of the landforms on Earth, um, there's change that does happen, right? That's the whole dynamic part of the planet, but not everything changes at the same pace. Some landforms might change pretty quickly over a few days, weeks, years. That's really fast in terms of uh, geologic time. Other landforms like mountains change at a much slower scale, tens of millions, hundreds of millions of years. Um, and so we need to be able to think in kind of both capacities, fast and slow. We'll go through that as we go through each of the chapters and talk about the different landforms. That will be part of what we talk about. But we also need to understand the geologic time scale itself, which spans 4.6 billion years, right? Earth formed about 4.6 billion years, and then here we are today. And there's a lot of stuff that's happened in between. And so, how we know that, what has happened in the past and when, we need, there's two different ways of understanding and coming up with that sequence of events. What's happened when, how fast or how slow. So, the two different ways we can understand this time and sequence of events is to talk about it in terms of relative time or relative ages. And this is simply putting events in order. We would use geologic clues to determine their order. But the relative ages is just their order, it's qualitative. It would be like saying, this thing, event A, it happened before event B. Another example here, fossils from the Ordovician are older than fossils from the Jurassic. But again, one thing happened first, and then another thing happened later. Um, and another example here is that I am the oldest of my siblings. Um, I could also say I was born first, and then my one of my sisters was born later, and then my other sister, she's the youngest. She was born last. Um, but that's the order. However, the with relative ages, we don't know how long ago something happened, and we don't know the timing between event A or event B. We don't know how much time elapsed between those two events. All we know is that one thing happened first, and then something else happened later. So again, you don't know how long ago I was born, or my sisters. You also don't know how much older I am from either of them. Maybe my youngest sister, was born just last year. That'd be impossible. But anyway, um, that's relative ages. That's what that is. Absolute ages is another way of talking about geologic time. And this is where we get our numeric ages. We this is a quantitative way of understanding events that have happened in the past, but we get numbers. So, an example here is that there's an extinction that occurred between the Cretaceous and the Tertiary eras. The Cretaceous here is represented in K, Tertiary is T. It's also called the KT extinction, just because it's so well known. This is this is when the dinosaurs all went extinct. That's this one. And so we can say that extinction happened 65 million years ago. That's what MA stands for. Millions of years ago. It actually stands for millennia annum, uh, or mega annum. What are those? Um, mega annum. Sorry. Uh, MA. Mega meaning millions, and annum meaning years. That's Latin. So in any case, we get a numeric age using absolute ages. With rocks, we use radiometric dating techniques to get ages. We analyze the rock. Uh, we the methodology tells us how old the rock is. These methods, though, radioactivity in general, wasn't discovered until the 1950s ish. Um, and so we didn't start dating rocks until, uh, 75 years ago. Again, relatively recent in terms of science. So it hasn't been around forever. We started determining the relative ages of events hundreds of years ago, using what's called uniformitarianism. But it wasn't until, again, fairly recently that we started getting these absolute ages for events and different types of rocks and fossils and things like that. Oh, to finish up the example using myself in absolute ages, that's me telling you that I am 44 years old. So you know how long ago I was born, and then I can say, oh, my sister is 42. My youngest sister is turning 40 this year. She's probably really upset about it. Uh, so anyway, those would be absolute ages because you know how long ago I was born, my sisters were born, you know how much time passed between us as we were born. So, yeah, that's the difference between relative ages and absolute ages. And we'll talk about why relative age dating can be very useful. Uh, I want to just talk quick. Hang on a sec. Yeah. We're going to relate relative ages to uniformitarianism. This principle was very important in developing the concept of relative ages as we can use it in terms of geologic time. So, kind of a catchphrase or a tagline for uniformitarianism is that the present is the key to the past. I'll explain that in a second, but I'm just going to mention that this phrase shows up in the first exam as well. So put a star next to that to make sure you know exactly the order of these words because it matters. What it means, the present is the key to the past. We need to understand the processes that are happening today in order to understand the past, in order to go back into the past and explain the things that we see um, in today's rocks and structures. Another way of putting this, and as part of uniformitarianism, is that uh, there is an assumption that the processes that happened in the past are the same as what are happening today. In other words, a river that was flowing 20 million years ago, which we can map out, um, that river flows the same way that rivers flow today. Um, they have floodplains. They start up in higher elevations. They meander across floodplains and they flood sometimes. And they move sediment and all of that stuff related to rivers that we observe today and we study today. We assume that that is they operated the same in the past, and we assume that because we have no reason to think otherwise. When we look at river deposits in the past, they look just like river deposits in the present. And so, in that way, we can explain the past. We can understand how the landforms were created by understanding uh, things that are happening today. So, uh, a different breakdown of uniformitarianism rather than just the present is the key to the past. I've got some other explanations here that um, this is the assumption that today's environment is operating or changing, has been doing so in the same ways throughout geologic time. And then we also have certain cyclic processes, which is essentially that we have steady state equilibrium, we have dynamic equilibrium, which is much more common. But in either case, we have these cycles for the systems that we encounter in nature. Um, for example, the trees in temperate climates, trees lose their leaves in cold weather, and then the leaves grow back in warm weather. That's a cyclic process. Happens every year in this case. It doesn't have to be every year, but in this case, it's every year. And then sometimes we have catastrophic events. I mean, an asteroid impact would be hugely catastrophic, but river floods would be considered as a catastrophic event. They don't occur cyclically. They can occur at any time, really. So it doesn't have to be this major sort of impact, although that would interrupt all other cyclic processes, but they can be more localized or regional, like a river flood. The system would recover, though, after a catastrophic event. Most systems would recover over some length of time. And then finally, well, I sort of explained this already too, that the systems operating today, similar to in the past. That is part of uniformitarianism. James Hutton and Charles Lyell are names that geologists are all familiar with because they were very involved in developing uniformitarianism and principles of relative age dating. So they're important in geology in terms of the history of the science. All this time I've been talking about uniformitarianism. We are referring to this whole 4.6 billion years, starting in the Precambrian and then heading into what's called let me pause talking about all that because we're going to talk about it next. But let us go ahead and watch here this video, also from AGI, the American Geoscience Institute. The video we watched in chapter 1 was Big Idea 3. This one is number 4, The Earth Continually Changes, which is appropriate. This is the Dynamic Planet chapter. So let's give this a watch.
Dude, little help here? Still stressing about the Bills game next week, huh? Here, try this.
This is Big Idea 4. Earth is continuously changing.
I'll turn up the volume.
Earth's geosphere changes through geological, hydrological, physical, chemical, and biological processes that are explained by universal laws. The changes to Earth's geosphere can be small, continuous, or only once in a while, and slow, or very sudden. Earth, like other planets, is still cooling, though radioactive decay continuously generates internal heat. This heat flows through and out of Earth's interior mainly through convection, but also through conduction and radiation. The flow of Earth's heat drives its internal motions. Earth's interior is in constant motion through the process of convection, with important consequences for the surface. Convection in the liquid, iron-rich outer core, and also Earth's rotation on its axis, are the two sources of Earth's magnetic field. Earth's magnetic field keeps the solar wind from stripping away our atmosphere by deflecting it around the planet. Convection in Earth's solid mantle drives the plate tectonic processes, such as the formation and motion of the continents and oceanic crust. Earth's tectonic plates consist of the rocky crust and uppermost mantle, and move slowly with respect to one another. New oceanic plates are constantly forming at mid-ocean ridges and other spreading centres. This plate then sinks back into the mantle at ocean trenches. Tectonic plates move at the rate of about 10 centimetres per year. Many active geologic processes occur at plate boundaries. Plate interactions change the shapes, sizes and positions of continents and ocean basins. The locations of mountain ranges, ocean circulation, and climate patterns. The location of earthquakes and volcanoes, and where Earth's resources and living things are found. Earth materials take many different forms as they cycle through the geosphere. Rocks form from cooling magma, the collection and solidification of sediments, and the change of older rocks by heat, pressure, and fluids. These three processes form igneous, sedimentary, and metamorphic rocks. Landscapes result from the dynamic interplay between processes that form and uplift new crust and processes that destroy and depress the crust. This interaction of processes is affected by gravity, differences in density, plate tectonics, climate, water, the actions of living things, along with weathering and erosion. Weathered and unstable rock materials erode from some parts of Earth's surface and are deposited in others. Because of the force of gravity, rocks fall and sediments are carried by water, ice, and air down to the oceans. Shorelines move back and forth across continents, depositing sediments that become the surface rocks of the land. Through plate tectonics and the action of glaciers, Earth's sea level can rise or fall up to hundreds of meters. This can cause shorelines to move out and back by hundreds of kilometers. The upper rock layers of most continents formed when rising sea levels repeatedly flooded the interior of continents. And that's Big Idea 4. Earth is continuously changing.
All right. So that video actually goes ahead of us a little bit because it started talking about rock cycles, hydrologic cycles, and plate tectonic cycles. So we'll get there um, in just a minute. But first, I had started talking about the geologic time scale, and I want to continue that thought since this time scale was formed largely through relative age dating. Now, since we've discovered radioactivity and can have absolute ages, some things have changed, but for the most part, we were able to develop this uh, time scale in terms of major elements, um, or major events, rather, just through relative age dating. In any case, um, how to read the geologic time scale may not be uh, incredibly apparent at first. And so I just want to explain a couple things about how we divide the time scale here. First of all, the column immediately, uh, or not immediately, but on the left, this is all of Earth's time. So 4.6 billion years, all the way up to today. This top of the graph there, that is today. And so some of the major splits of time start off here on the left. These are eons, and they are our largest and longest um, divided time. The Precambrian includes all time between 4.6 billion years and 541 million years ago. That's the Precambrian eon. Now, because that is so long, we have actually split it into three other eons: the Hadean, the Archean, and the Proterozoic. Um, Hadean, um, just to explain their names a little bit, Hadean refers to Hades or hell. And it's given this name because the conditions of Earth during this time, 4.6 to 4 billion years ago, was very hellish, we think. It was full of erupting volcanoes, magma oceans. That term gets thrown around. Constant changes, very hot. Um, Gases being released from these eruptions. Not a very nice place during that time. And then we have the Archean. Archean just kind of means old, like archaic. Um, so that's just given a name for how long ago it happened. And then we have Proterozoic here, where proto means early or beginning, um, or before. Or did I say that already? Sorry. Zoic, on the other hand, that means life. And so the term together is really meaning before life. Now, that's not quite exactly true. We'll see in a second. But um, there was not a lot of life during these time periods. Um, we had prokaryotes and eukaryotes developing as the first life on the planet, and other bacteria, cyanobacteria. We had those occurring. There's jellyfish and just really simple single-celled life to jellyfish, marine worms, and such. That's all the kind of life that existed in these two eons. So Proterozoic before life, well, it's before most life. And then the Phanerozoic eon, this is where life really starts to explode. Um, and we have the diversification of life. That's when that started, the beginning of the Phanerozoic. Those are eons. Eras, the eras here are in this column, and they are just divided eons. So we have early, middle, late in our Precambrian as our era divisions: early Proterozoic, middle Proterozoic, late Proterozoic. That's how you'd read that. Then in the Phanerozoic, there's three eras: the Paleozoic, Mesozoic, and Cenozoic. Um, those are eras. The next uh, splits of time, those become periods. We split the eras into different periods. And so that's what we're going to look at in the column here on the right. The eras are repeated here, are three different eras: Paleozoic, Mesozoic, Cenozoic. And then the periods are listed here. The Carboniferous period is split into two different also periods, Mississippian and Pennsylvanian. But yeah, all of these splits are periods. The Paleozoic, we start in the Cambrian. There's something called the Cambrian explosion, and that is where a whole lot of life started diversifying right here. Um, so we have a handful of Paleozoic periods. I'm not going to read them all to you. We have the Mesozoic periods, which most people have heard of, Triassic, Jurassic, and Cretaceous, because dinosaurs. Of course, those weren't the only things alive at the time, but um, in any case, then we have our Cenozoic periods, the Paleogene, the Neogene. They kind of get the same. Uh, they were once together called the Tertiary, hence the Cretaceous and Tertiary boundary. But for different reasons, we've split them into Paleogene and Neogene, although some people still refer to this as the Tertiary. In any case, the most recent period that we are in today is called the Quaternary. So those are our periods split from the era. And then last thing that we'll go over, there are other splits beyond this, but um, not important for us. Periods can be split into epochs. And so you might recognize the Pleistocene, maybe. This is the last ice age, or as what we refer to as the Ice Age period, when there were, the woolly mammoths and the saber-toothed tigers and all the Ice Age movies are taking place here in the Pleistocene. How many of those Ice Age movies are there? There's got to be like 20 of them by now. Um, Today, though, we are living in the Holocene epoch. And I'm just going to skip here down to the bottom of the slide. Our most recent epoch. We are in the Holocene. There's been talk among earth science around the world uh, about creating a new epoch for what we live in today, and we would call it the Anthropocene. This term has been kicked around for a long time, decades. And it was the idea of it is based, or we can maybe suppose the base, the what do I want to say? Why some people wanted to create the Anthropocene based on its name. Um, Anthro, if anybody is familiar with this anthropology, anthropomorphic. If you're familiar with either of those words, you might be able to guess what this um, refers to, this word Anthropocene. It is based on humans. Anthro means human, essentially, people. So anthropology is the study of people in the past. Um, Anthropomorphic means that something is human-like. Uh, when we look at anthropomorphic cartoons, the animals, like in what's that, Zootopia, those are anthropomorphic animals. Those animals are essentially people, um, looking like people, standing upright and talking. So that's anthro is where this idea of an epic named after people is the idea that we have changed Earth in a way that deserves its own epic. Earth is changed because of people in a way that it deserves its own epic. And so some of the reasoning behind this is things like uh, air pollution, one, um, the drastic increase in CO2 in our atmosphere, uh, uh, garbage, trash. We have all of our landfills. We've got all the plastics that stick around for I forget how long. Um, Plastics in the ocean, things like that. People, oh, they came up with the word um, a plastiglomerate. or something like that. Plastic conglomerate. Conglomerate is a type of rock, and I I really hate that term, plastic glomerate, because because rocks are made of minerals, and minerals, by definition, are inorganic, and plastics are not. Plastics are made from they're byproducts of oil, and oil comes from living things. And so I just and plastic's not a mineral either. So I hate it on so many levels. And maybe you can guess my opinion on the Anthropocene and coming up with a new epic. More recently, I'll say more recently, there was actual movement forward on the Anthropocene, and in the last just few years, it went to a global committee to review um, their submitted documents and their pros, why they wanted to, why naming the most, why coming up with a new epic was a good idea. Um, and all of that was reviewed, and it was not approved. And so I was kind of happy about that. I don't, I just kind of balk at the idea of a new epic called the Anthropocene after humans. It's like, how narcissistic can we get? Uh, and I say it's narcissistic because yes, we have had a a large impact on the planet. Remains to be seen how long that would persist into the future. And we just haven't been around all that long as a species. And so to want to name a whole new epic after ourselves is um yeah, I don't like it. Like I said, it feels too narcissistic. Um and who knows how long our species will, persist. Uh, so anyway, it wasn't approved. They might come back and come up with some other reasoning why it should be, but for now anyway, nobody liked it. Or enough people didn't like it. Okay. Going back to the geologic time, something that I mentioned about when life came about and what was going on in the past. That I want to use those sorts of events to understand how long geologic time really is. It's also called deep time because it goes, well, all the way back to the beginning of Earth, but it's billions of years. And our brains can't quite comprehend how long that is. I mean, some of us can't even comprehend what next year will look like. Or for me, it's usually like in decades. I'm like, okay, a decade from now, I can't wrap my head around that. Um, but we can go back hundreds of years. We can more or less understand, our ancestors a couple hundred years ago. We can have some concept of that. But geologic time is going back millions of years, and events themselves taking tens of millions of years. So to help us understand the geologic time scale a little better, I want I a way to do that is that you can imagine putting all of um, the events that have happened on Earth, including the beginning of Earth, all the way up to today. We can put all of those events on a 1 year calendar. So, right at January 1st, right after the ball drops, that is the moment Earth formed. Boom, Earth. And then the end of the calendar, uh, New Year's Eve, just like right the second before the ball drops, that's where we are at the present. Everything else fits in between, and we have our whole time scale on the stretched across 1 year. I hope that makes sense. Earth formed here, and the Precambrian starts here as well. And there's not a whole lot happening in January, February, March, April, blah, 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 all the way to November. That much time, not much is happening. I mean, there are major things happening. We have the formation of rocks, the ocean, the atmosphere. We have simple life developing. I mentioned prokaryotes, eukaryotes, and cyanobacteria. Those were developing single-celled organisms and whatnot. But that's it. That's it over the course of 10 months of the year. 10 months of the year. And just this is happening. November 8th, about first week of November, we get marine worms and jellyfish. So more complex life. The end-ish of November, fish. This is also right around the Cambrian explosion that's occurring. Cambrian explosion was probably a few days ago, a few days before November 21st. So again, like all of this is the Precambrian, 10 and a half months of the year. The last two and a half, no, 1.5. I don't do math in my head. Um, anyway, these remaining months, 1.5, um, are all in the just Phanerozoic. And so, yes, again, we have fish in the ocean with more complex ocean life occurring in these couple weeks. Then we start to have land animals. The first land mammal or land animal happened probably a few days before December. So we have land diversification, insects and amphibians. And then all this other life occurs, dinosaurs at some point, they go extinct, blah, blah, blah. Uh, the first modern human, this is where I'm getting into people being narcissistic about our importance here, because people don't show up until the last day of the year, about 12 minutes to midnight. So these are just the early Homo sapiens, and Neanderthals and Australopithecus and all that. They came right around the same time. So 12 minutes is how long people have been around. And then more advanced life and society and, all this recorded human history, that's the last 30 seconds of the year. So imagine 30 seconds of the year. We're going through a whole year here in 2026, right? All these things we're going to be doing all year. Um, the last 30 seconds before midnight is how long humans have existed on the planet. And so, anyway, the point is, it's not very long. It's a short period of time. And to name a whole new epic after us, I, yeah. Make up your own mind, though. You can have your own opinion. I have my opinion. That's what science is about. Okay, so a quiz question. Um, as we did in chapter one, I'm gonna leave this up here for you to think about it. If you want to pause, um, you can do so now. But yeah, here's one of the review questions. Which of the following is not an example of a landform produced by endogenic processes? Not an example. Faults, which cause earthquakes, volcanoes, mountains, or rivers. Okay, so I assume you paused it if you wanted to already. So the answer is rivers. The other three are formed by endogenic processes, meaning heat coming from the inside of the earth is what is fueling those processes. Rivers, on the other hand, they flow on the surface, and changes to rivers occur through exogenic processes. So that's the first quiz question. Um, and yeah, I think we'll just stop here for the end of the first video of chapter 2.